Hi, everyone, and thank you for watching my talk and listening to it. My name is Manuel Buen-Abad. I'm going to tell you a little bit about a project that I did with Gigi Fan and Chen Sun. Here's the archive number. It's going to be on the bottom right of every slide. I'm a postdoctoral Brown moving on to UMD, Maryland. And as always, it's a great pleasure to be in Cosmology from home. So let's take it away. As you probably know, in most axion and axion-like particle scenarios, there is an axion-photon coupling, which leads to the very interesting phenomenon of axion-photon conversion. So let me explain a little bit about what this means. So imagine you have a light source here represented by this yellow star emitting photons, gamma, represented by the wavy red lines. And you are an observer, right, looking at this light source. Now, if these photons travel through a medium that has a magnetic field, B, if there are axions and axion-photon couplings with J, gamma, gamma, represented by these green circles, you can expect the phenomenon of axion-photon conversion. So this axion-photon coupling looks like this term in the Lagrangian here, and this Ga gamma gamma, this axion-photon coupling, has dimensions of 1 over energy. So just from dimensional analysis, Feynman rules and just heuristics in general, you can calculate what's the probability of some of these photons to convert into axions, and this axion-photon probability conversion given here heuristically by Ga gamma gamma times the strength of the magnetic field that through which these photons are traveling, square. And from this you can find out that this has dimensions of energy square, and therefore this has dimensions of length squared. This quantity you need to multiply in order to get this probability. And in some limit, this x here, this length, is precisely the distance that the photons have traveled through the medium. But in general, it is just a more complicated expression, right? So just to summarize, then the axion-photon complex, which has dimensions of 1 over energy, can lead to axion-photon conversion for the case of photons traveling through a medium that has a magnetic field. Now, as a result of this, some of these photons being emitted by the light source will be converted into axions, which make it to you, the observer. And since the axions are fairly invisible or have very weak interactions with the standard model, then what this ends up looking like is that the flux of light being emitted by the source is being dimmed. That is to say, not all that light is making it to you, the observer, as it travels through this medium with a magnetic field, but some of it gets lost in the form of axions. So as a result of this, the light source looks dimmed, which can be interpreted as thinking of the light source as being farther away, right? Because the farther away a light source is, the dimmer it looks like, right? So in other words, you have this combination of different factors, right? If you have axion-photon conversion, your light source is dimmed by the conversion of photons into axions, and therefore it looks like the light source is farther away. So if you have access to all of this knowledge, right? If you have access to how to measure distances to light sources and to measure their fluxes and how bright they look like, whether they're dim or not, you can therefore use all of these ingredients to put constraints on axion-photon couplings, right, through this mechanism of axion-photon compression. So there's a very interesting playground where we can look at this, and that is a cosmos, because we have all the ingredients that you need here. You have a bunch of light sources. Here's just a picture of very nice random picture from Hubble telescope with a bunch of light sources, stars and all sorts of interesting things going on. You have light sources. You have magnetic fields. There are magnetic fields in the cosmos, and there are magnetic fields in our galaxies, clusters of galaxies, etc. And we have access to measuring distances, right? Well, that's what cosmology tells us, and that's what the metric is about. And Einstein tells us that that metric depends on the energy content of the universe, etc., etc. So the cosmos, the universe, is a very nice playground, a sandbox in which to look at axion-photon conversion, which we can therefore leverage in order to constrain axion-photon couplings, right? Once again, magnetic fields, light sources, and measurements of distance, right? These are 3 ingredients, and that's what we set out to do in our paper. So first, a few words about one of these ingredients, namely magnetic fields. Like I said, there are magnetic fields in our galaxy, and they are well understood, and they have been measured. There are magnetic fields in clusters of galaxies, and they have been measured, and they are reasonably well understood. There's still some debate in the community and the experts about how well you should model this. How well can these magnetic fields in the clusters can be modeled, whether they're turbulent or regular. But they're reasonably well understood, and they have measured. And finally, it is hypothesized that there are also magnetic fields in the distances, in the vast expanses between clusters of galaxies, which are large structures. So these vast expanses, these vast distances, are called the intergalactic medium. So it is hypothesized that there are magnetic fields there. In fact, we have upper and lower bounds on how strong these magnetic fields ought to be. And you can look at some of these references here in order to learn more about this very interesting field its own, magnetic fields in the IGM. Like these magnetic fields could have different origins early in the universe through inflation of phase transitions, or late in the universe through outflows of galaxies. Like I said, these have not been detected. There are upper and lower bounds on the strength of these magnetic fields. A commonly used benchmarks are the order of nanogausses for the strengths and coherent lengths, right? Like the domain sizes for these magnetic fields of order megaparsecs, but there could be some variations on this. So this is the one ingredient that is a little bit on less firmer footing in the case of the intergalactic medium, IGM. In our galaxy, very well understood. Inside clusters of galaxies, reasonably well understood, and they have been measured. It's just in the case of the IGM where things are a little bit more floating. So enough about magnetic fields. Let's move on to the other two ingredients, namely light sources and distances. Cosmologists use different ways to measure distances. One of them is luminosity distance, and these these measurements rely on having access or knowledge through some way of the luminosity of a particular astrophysical object. For example, supernovae. So let's say there's a standard candle. This is what they call them. It's an astrophysical object who shines and is bright, and you know through some mechanism how bright it is. It's luminosity, right? Supernova type 1a or some common use standard candles. Now, if you know this luminosity, you can go ahead and measure the flux of photons coming from this light source through the inverse square distance law. You can relate the luminosity in the flux, and this distance that is involved in this relationship is called luminosity distance, right? And this luminosity distance depends entirely on the geometry between you, the observer, and the light source that you're looking at. And according to Einstein, this geometry depends on the energy content in your universe, in your cosmos, right? The energy density, the pressure, etc., what sort of stuff is in between you and the light source. And this is a formula, and this is how you can obtain the luminosity distance, and you can see that it relies on something else. In the case where in your cosmology, in particular lambda-CDM, where the number of photons is conserved. However, if you have axion-photon couplings, like I said in the beginning, the axion-photon coupling can lead to the dimming of this light source, and that, in other words, not all of the photons from the light source are making it to you, the observer. Some of them are being converted into axions, right? So you need to correct this flux computation by multiplying by the survival probability, which is just 1 minus this conversion probability. Right. So the flux in the case for luminosity distance, in the case where you have some standard cosmology like lambda-CDM with the addition of axion-photon couplings, looks like this. And from here you can learn, you can read out an effective luminosity distance, which is given by all the luminosity distance divided by the square root of the survival probability, right? And as a sanity check, the survival probability is smaller than 1 divided by the square root of that gives you a number larger than 1, because this quantity is dimming, smaller than 1, dimming the flux, and as a result, the effective luminosity distance is larger than the vanilla luminosity distance, because a light source that is dimmer looks farther away. So everything fits. Very nice. This idea is not new. It's 20 years old from Chucky, Caliber, and Turning, where they tried to get rid of the cosmological constant, back with the cosmological constant, by using this Axion-photon conversion and mimicking the effect on luminosity distances measurements. Now we know the cosmological constant exists, and it's here to stay. So we don't need such a large effect as these people that required 20 years ago. But if you have Axion-photon couplings, you have magnetic fields, you will have this phenomenon. So you can still use this to put constraints on Axion-photon couplings in the way that I'm going to show you now. On the x-axis, I have a redshift to different astrophysical objects. On the y-axis, I have something called the magnitude, little m, apparent magnitude or apparent brightness. And this is essentially logarithm base 10 or log base 10 of the luminosity distance. And to what objects, to what astrophysical objects? 1,048 little gray dots here, which represent 1,048 supernova type 1a in the Pantheon dataset. This is the most recent collection of measurements of apparent magnitudes or apparent brightnesses to supernova type 1a. And here they are. Analyze the y-axis in such a way that 0 represents agreement with a fiducial value for some cosmology. Lambda-CDM, a fixed value of Hubble to some 68 or something like that, and the value of the cosmological constant to something. It's not important, the details. The important thing is that 0 represents agreement with a fiducial value for a cosmology that is just pure vanilla lambda CDM. So the blue what you would have for this apparent magnitude, which is the log base 10 of the luminosity distance, the effective luminosity distance when you have lambda CDM with an axion-photon coupling of order 10 to the minus 12 inverse GeV. In other words, you have lambda CDM, base lambda CDM, but you also have axions coupled to photons with these strength couplings. And you can see that this blue line passes through 0, which means that it's in perfectly good agreement with lambda CDM, base line, vanilla lambda CDM. In other words, lambda CDM and lambda CDM with axion-photon couplings of order 10 to the minus 12 inverse GeV are indistinguishable, right? And they produce exactly the same chi-square fit to this data set from Pantheon supernova type 1A. However, crank up the coupling 10 to the minus 11 inverse GeV, sorry, you get the red dashed line, and you end up with a severe disagreement with this line from 0, right? This fiducial value. And you end up missing a lot of these gray dots and producing a poor chi-square fit to the data. And therefore, you can use this luminosity distance measurement to supernova type 1A in the Pantheon dataset to put constraints on the axion-photon coupling. And that's precisely the idea, that we're using cosmic distances, luminosity distance, to put constraints on the axion parameter space, the axion-photon coupling, right? So just like we did for luminosity distance, there's a different kind of distances that you can use in cosmology. Angular diameter distance. Now, this relies not on how, in principle, it's not relied on how bright something is, but how physically big something is. Right? So it doesn't rely on the luminosity on the object, but it relies on its diameter, hence the name. So if you have access to, through some means, to the diameter of a physical object, and you look at the angle of substance in the sky, you can take the ratio of that diameter to the angle of substance in the sky, and you find out the angular diameter distance to that astrophysical object, right? So this is something people use, for example, for BAO baryon acoustic oscillations. You can look at the clustering scales of galaxies in angles in the sky. You can have access to what the clustering scale is from your theory of the evolution of the cosmos, in particular the sun horizon at the epoch of baryon drag, and therefore you can calculate angular diameter distances, right? So this is in general entirely geometric, right? It does not rely on any brightnesses, except in the case of clusters of galaxies. In fact, there's a method developed in the late 70s, early 80s, where you can calculate the diameter of a cluster by looking at how bright it is in CMB, in Sunyaev-Zeldovich effect, and the X-rays. So I don't have time to go into all the details, but basically is you can find the diameter and hence the angular diameter distance to a cluster of galaxies by looking at the intensity of how bright it is, this cluster, in the Sunyaev-Zeldovich. What does that mean? The CMB photons coming from early in the universe passing through a cluster will see the plasma inside this cluster in what is called the ICM, the intracluster medium. And these CMB photons get upscattered, producing a spectral distortion, which is called the Sunyaev-Zeldovich effect. So this intensity is represented here by the ISZ. And this cluster also has this ICM, this intracluster medium, has temperatures of order kV, so it shines in X-rays. So you can also look at the cluster in X-rays. So you take this ratio, you can find out the angular diameter distance to that cluster, up to some factors that are not important. And this is the formula that you would have in your standard cosmology if the number of photons is conserved. However, since you have axion-photon couplings, you should not expect this in general to be the case. And you need to play exactly the same game, right? Correct the Sunyaev-Zeldovich effect intensity by multiplying by a survival probability for the Sunyaev photons or the microwaves, and you need to multiply as well by a survival probability in the case of the photon, the ICM, intercluster medium. So as a result, you have an effective angular diameter distance to a cluster of galaxies that depends on the all angular diameter distance up to some corrections from survival probabilities. And you can play the same game as before, where you have the x-axis, the z redshift, y-axis, you have angular diameter distances normalized to some fiducial value from lambda CDM. The 38 gray dots here represent 38 angular diameter distances to 38 galaxies by the Buen-Abad collaboration, 2004. And the blue and red lines represent exactly the same case as before, where you have not just lambda CDM, but lambda CDM in addition axion-photon couplings over their 10 to the minus 12 inverse GeV or 10 to the minus 11 inverse GeV for the blue and red cases, respectively. So the blue case passes through 0, perfect agreement with lambda CDM, indistinguishable from lambda CDM, vanilla lambda CDM. the case of the red case, where the coupling is another magnitude larger, 10 to the minus 11 inverse GD, you end up missing a bunch of gray points. You miss the zero line, so you can actually distinguish between vanilla lambda CDM and lambda CDM with axion-photon couplings of this strength, and produce a poor fit to the chi-square fit to this data, and therefore you can constraints on this axion-photon coupling. So once again, you're using luminosity distance, and you're using, in this case, angular diameter distance to put constraints, and they have different expressions because they have different survival probabilities, and therefore you can get rid of some degeneracy and put very interesting constraints. Now, a little bit of an aside, right? In Euclidean geometry, obviously the angular diameter distance and the luminosity distance are the same. Our cosmos is non-Euclidean, so in general in cosmology these two quantities are different. So that's exactly what we set out to do in our paper. We look at cosmic distances, we model them, and in the case of lambda CDM with the presence of photon couplings, there are cosmological parameters such as Hubble parameter, the cosmological constant, the luminosity of the supernovae, the sample drag, because it's going to be important if you include BAO data sets, as we do, to get rid of some degeneracies, axion-photon coupling, J gamma gamma, and the mass of the axion, right? We scan this parameter space with MC, the publicly available code, and do different MC runs, which include data sets from Pantheon, supernova type 1A, 38 clusters from Bonamente, BAO measurements, and we anchor the Hubble parameter with early or late universe. As you probably know, there's currently a crisis in cosmology about what value of Hubble you should take. Early universe gives certain value of Hubble, and late universe measurements such as shoes and TD Cosmos give different values for Hubble. So we sidestep this issue by doing separate fits for early or late universe, Planck 2018 or versus shoes TD Cosmos. We do runs with different IGM properties that I haven't got the time to tell you about, and we consider we either ignore conversions inside the clusters, not just in the IGM, or include set conversions in our fits. And all of this is available on my GitHub. So here are the results, and the x-axis is the axion-photon coupling. And in red lines are our constraints in the case of conversions only of photons as they travel from the light source to you, the observer, through the IGM, assuming a magnetic field in the IGM of order 1 nanogauss. Using these constraints to scale up and down. The solid line and the dashed line are late universe measurements for Hubble or early universe measurements for Hubble, shoes, and TD Cosmos versus Planck 2018, respectively. You can see that they basically agree with each other. If, however, you include conversion of axion-photon couplings inside clusters of galaxies, which I haven't had the time, but basically what you're having is something similar, right? Some photons, as they're being produced in X-rays inside a cluster of galaxies, convert with the magnetic field inside the cluster, not in the IGM, but in the ICM, not in the intergalactic medium, but inside the cluster. This bolsters the constraints, make them another magnitude stronger by the way of the uncertainties in the IGM magnetic field, because this completely take over, and they are very competitive compared with other constraints in the literature. Now, there's still some debate, like I was saying, about what these magnetons look like, whether they're regular or very turbulent. You know, modulo that debate. This is what these constraints are or look like. So just to conclude, therefore, you can use cosmic distance measurements to put constraints on the axion-photon coupling. In the case that you consider exclusively axion-photon conversions in the IGM, the intergalactic medium, the vast expanses, vast distances between clusters of galaxies, you can have strong bounds on J gamma gamma, the axion-photon coupling, for masses less than 10 to the minus 12 electron volts for a commonly assumed benchmark of more than 1 nanogauss for IGM magnetic field. Obviously, this magnetic field can scale up or down a little bit. It's a little bit unclear how exactly how strong this magnetic field is, although there's upper and lower bounds. If you look at the fact that the solid lines and dashed lines, there's very little differences between them, it turns out that our constraints are entirely independent of crisis, right? It depends really on Hubble as a function of redshift and not really the absolute scale. If you include the magnetic ICM conversion, the conversion inside clusters of galaxies, the bounds get stronger. That's the blue line. They're independent on the uncertainties and the IGM. There's some debate about what the ICM magnetic fields ought to be like, but here we have it. And finally, things can only get better. Either we get better measurements of the shape of Hubble as a function of redshift with a Pantheon 2.0 data set, for example, or we can determine exactly what the magnetic field ought to be in the IGM or in the ICM, and things are only going to be better, either push down or the bounds get on firmer footing. Thank you very much for your attention, and I'm happy to take any questions later on the discussions.